Hello everyone, it's October 7th. Change the setup a little bit. Well, I actually already solved the problem last night. It's number 79. I mean, it was 79, so I must have done it before. Back in 2019, if I remember right. Oh, many times. We did in 2019 and 2020. They're recycling the problems. I don't know if I like that. All right, I don't know if I like that. They're recycling problems. I like to do new problems, right? New problem. But anyway, uh, the benefit of this is just keep practicing. So it doesn't really matter if it's old problem, new problem, because problem you've done many months ago, you forget. Like I don't remember this one at all. So let's take a look. Given a n by n grid of characters that's on a board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So the board is this, okay? And then A, B, C, D, E. Isn't this, can we do, let's see, word length is M, N, and 6. Lowercase and uppercase English letters. Can we, hold on. Are you saying we have to start from every single position? Uh-huh. Okay, I'm listening. So we start from this position, we can get all types. I mean, each position can only get, like this position can only get this one, right? So everything that this one can get can be appended to this. Everything this one can get can append to this, right? And then for this one, we're talking about this is the starting point, right? This is a starting point that we have. Oh, but everything can only be used once, right? Oof. So we're saying for B, right, then we can say everything that starts from C. Well, it starts from C, that means it does not go back to C. Everything starts from A, that means it doesn't go to B, right? It starts from C, but doesn't go to B. It starts from F, but doesn't go to B. Okay? So we start from a position, right? And then we look for 4 directions, because it didn't really say the order, it's just any order. So we look for 4 directions that we have, and for each direction we also need to put in like the previous value, the ones that we came from, so we know we don't go back that position. So everything starts from here, but does not go back here. Directions, which means if I'm here, I say I want to know everything that starts from C except from this direction. So I need to pass in a direction that C cannot go. Okay, and then I go all the way that we check every single one of them. I mean, for every one, I have 4 or whatever directions I can go, right? So if I find those directions, everything that that direction goes. But also, if I go that direction, it cannot come back to me. Hold on. I don't. How do we search? Because the question is asking if it's true or false, right? And the word is A, B, C, C, E, D. So we need to find A, right? So we have A, we have 2 positions for A. But think about it. We have only 6 by 6 max, right? So we look for A for all the position that has A. And then we look for all the position that have B. Then we look all the position that we'll look for all the position that has A, and from A we need to search for see if A has any B. Like this A doesn't have B, so this one is no go, and this one has a B, so only one B. So we keep going. So currently we're looking at B. So the next one, right? The next one, we have all these positions. We have these 3 positions, and then the next one must be. Yeah, we just okay. So from a position, so we start from looking through all the starting positions, right? And then for each of them, we're gonna run a search. And to run the search, we just look around, right? Look around. And if I have one, then I just keep searching that one. I keep searching. So that will be a DFS, right? That will be a DFS. So in this case, we'll first find S with an S with 2S. And for each S, we start searching, right? We start search. So the DFS will be just, let's call it search. So given the current that we know is good, we call search. So we have an S, and then the target will be the next one. So when you look around, if we have an E, right, then we're passing this and go for the next one. And this one we need for A, we have A, right? And then B, let's go C, but there's no more B. Now we cannot go back. How do we know we cannot go back? Well, we are at C, and we say the next one is B, and then we look, yeah. So we have to keep track, right? We have to keep track. Okay, I think this might work. So let's do this. 7. Alrighty. Alright, let me just minimize this. Okay, so I think this shall work. I'm not 100% sure. Alright, let's go back here. Oh, shoot. Okay. So the ideal is we need to find, so we're going to go through the board to find the potential start. So potential start can be this, right? And then we're just going to go for row in board, right? And then for letter in row, we need a position. Dang it. mn equals len board and len board 0, right? So we go the old school for I in range m, for j in range n, we're going to find the starting position. So say if board ij, right, if board ij is equal to word 0, then we record potential start dot append. It's called ij, right? Once you're done, we say if not potential start, when the return false immediately. Now we have, so we're going to def search. Search, we need I, we need j, and we need index. That's for the word, and we need the path, right? We need the path. So we don't. So path is going to be a. Oof. Maybe we can use board to signify this because we're searching, like backtracking, right? So we simply just turn the letter into, yeah, because every time we only search one path, right? So we can turn that, yeah, we can use the board. We don't have to, we're not returning anything. No, we're returning a Boolean value, right? We're returning a Boolean value. Okay, so we have ij, and then we have the next index. So ij is the current value, and we need to look around, right? We look around. So when do we end? Well, if index equals to len word, right? that means we found it, then we return true. Otherwise, we're going to say for ni and j, right, in 2, 3, 4 directions, right? So 4 directions is going to be I plus 1 j, I minus 1 j, I j plus 1, and I j minus 1. So 4 directions. And if 0 smaller equal to ni smaller to m, and 0 smaller equal to nj smaller to n, and ni and j not in, oh wait, and would ni and j is not equal to pound. We use pound to indicate that we have searched that one before. So not equal to pound, right? Okay, so so we're searching for ij, right? So we need to turn ij into, when do we turn that into the pound? We search for this, we turn that into a pound, right? And after we finish search, we're going to return it. So I'm going to say current equals to board ij, right? And then board ij equals to pound. That means we have visited this one, and I'm going to look for the next. So we go all this and oh, we can directly do this. If I set to this, and it will definitely be, yeah, we can just say it has to equal to word index, right? If it's all good, then we're going to search ni and j index plus 1, right? And this one we're going to say what? If this is true, then return true. If it's false, right? If it's false, then search for the next one. Search for the next one. If all come out is bad, then board ij coming back. So it's backtracking, right? Coming back to this, and then return false. And just for the sake of it, so we're gonna say from tools import ARU cache. I'm pretty sure we need to cache this. So when ARU cache it, max size is none. So we'll search, and then what we need to do is for PS potential start in. Now we just say for ij in potential start. We can actually say return any, right? Any such ij. Oh, I just realized something. We have to rebuild the cache every time we do it. Like if I achieve some in the past during the cache, you know what? I don't like it. I don't like it at all. I think I will just do the cache myself, do the memo myself, because we are checking every single one, right? If I have a lot of potential starts, it helps. Hold on, let me think. So we're checking this position, and we're checking certain position, and then we're looking for the next one. If it's the same, yeah, we should cache it. But if we do every single one in the potential starts, then the problem is when we call the search from fresh every single time, then the LRU cache will not work. It only works when we're doing this. Therefore, I would like to change this. So it's going to be a 3 level. All right. Yeah, I like to change this memo. Change the memo. So what does the memo look like? Oh, ij and index. I mean, what it can be is ij index. What's the word length? 15. So it's a small, right? It's small. So we can do. All right. So inside will be. Let's call it false. All right. Let's call it false times n for underscore in range m. Right. That's a m by n, and for underscore in range index plus 1. Right? Index plus 1. Okay, so that's the memo. And then we say if this, so we don't return. Now we don't return. So we return nothing. What we're going to do is, oh, false, true. That is, yeah, it's going to be none. None. So we're going to say if, right, if memo, right, memo index I, j is not none, then return. Yeah, yeah, I think we still return. We still return. Let's still return. It's easier to handle if we still return. So if it's not none, we'll just return memo index I, j, right? Otherwise, we say if this is this, then we say memo index ij equals true. All right, equals true. Nah, I don't know, man. Equals true, and then we return true. I feel like we don't have the return, right? And if we, let's say, no, let's return. Let's return. So we set it to true, and then we return true, right? And then we say blah blah blah. And when I say search, if this is true, then we're gonna set this one to true, right? We set this one to true, and then return true, right? Otherwise, we return this. We're gonna set this one to false, and return false. So we set my own memo. And the benefit is that when we do the search, we can use the same memo. So we're gonna say, I'm gonna search ij. Well, we already searched the first one, so index will be 1 for I, j in potential start. Excuse me. All right, let's try it. What do we have? 3 tests. Let me just try it there. Then we don't use IO cache. Okay. Console. Use example test case. Let's try it. Index is not defined. Why do you say index? That's not index. That is len word. Len word. Okay. So try it again. Pending. None type is not subscriptable. Did I do something wrong? Yeah, you did. I think this messed again. String index out of range. How? How? Alright, this is a bit serious. We need to debug this. Let's debug this. So, test case. This one we have to. A lot of things need to handle, right? Yeah. So it's these two things, and this is true, right? So that's that. So we can just do it easy. We can do. I know. So we can do the next one. Oh, the exact same, and we just change. Okay. So it's the exact same thing. So we just change the word. This is CEE, and this I think is ABCB, right? ABCB, and this is false. Now is magic. Select this, and then change to this, and then select this, change to this, and coming back. Okay, and this one will be board and word. Board and word. And this is exist. Board word. Okay. Yeah. Search in this index plus 1. It says here. Well, we do go along, but I have this check. I say index is not none, and I return this, right? And then this index is none, and I check this. If I check this already, why would this still be wrong? Alright, do this, and then we're just going to print, let's print here, print ij index. So 0, 0, 1, 1, 0, 2, and 2, 0, 3. Word has what? 0, 1, 2, 3, 4, 5. 5. Hold on, which one? Oh, word. Damn, that's bored. My bad. My bad. That's bored. Come on, man. Come on. There we go. True, true, false. True, true, false. Alright. Let's try it. Go. Last time is 168. Error. What's the first error we have? We got, we do have error in the past. Okay. What the hell is this? Okay. It's supposed to be true, but I report false. That's concerning. Because last time we did it, but this time we did not. I don't like how this one's going. Alright, let's see. Where did we go wrong? Let me draw this. have 3 rows, right? And then 4, 1, 2, 3. A, B, C, E, S, F, E, S, and then A, D, E, E. Oh, I think I know. I think I know. I think I know. I didn't backtrack. When this is done, I did not backtrack. Can we backtrack? If it's true, then we do this. Yeah, we need to backtrack. So we need to do, this is true, and then backtrack. Why we backtrack is still wrong? Because that's not a problem. Yeah, we definitely need to backtrack, that's for sure. So we set this, because we initially set this, and then we go all the search, right? And when the search is good, or the search is bad, no good, no good, no good, will come in here, we set it back. If it's good, and we also set it back. Let's see, starting point. Rest equals this, and then, you know what? Let's say for ij in potential start, print search ij1, right? And then for row in board, print row. Well, that's fine. Everything is under control. All right, A, B, C, E, S, E, A, B, C, E, S, A, B, C, E. All right, S, E, 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 F, S. Yeah, it shall be right. Where did we go wrong? Search the next position. I have only 2. One of the position is wrong for sure. For the first position, hold up. Let's see. Let's print ij index. Let's see what happens. So ij001. That's the start, and then the other one is 0, 0. The other one is 0, 3, and 0, 3 is no good. 0, 3. No, it's not 0, 3. 2, 0. This is no good, so that's good. So this is what we have, right? So from 0, 0, 1, then 0, 1, then 0, 2, and then 1, 2. Okay. I mean, that's fine. 4, 5, 6, 7. We didn't go to 0, 1, 2, 3. We didn't go to 0, 3. Did we go to 0, 3? We did go to 0, 3. The 0, 3 is a 6. And 0, 3 is 4. Yeah, this is wrong. 0, 3 is 4, right? 0, 3, 4, because we go A, B, C, E. Yeah, 0, 3. Actually, no. Oh, yes, yes, yes. 0, 3, 4 is the next one. 4. Then we shall go to 1, 3, right? We shall go to 1, 3. And 1, 3, we have 5. Oh, I see. 135, I hit it already, but previously when I hit 135, it was false. But now it's dependent on the previous state, which means we shall not memo it. It's dependent on the previous state because the previous path, like we can end up at the same position, right? But if the previous path is different, then there's no way. Like the result we get for a position is dependent on previous path. It's not independent. If it's independent, we can memo it, but it's dependent, so we cannot. Which means if we comment out this and just we just remove all the memo talk, the stupid memo talk. But we still need this. We need backtracking because on each path we need to do this, right? And then on each path we can memo it. Can we memo it on each path? No, because we'll hit a different path. Again, like we hit the same spot, but can't come from different path, and they should not be the same. So we do not. We do this, so we just no need this, and no need this. Yeah, there you go. So cannot memo. Memo is not correct. Which, I mean, honestly, make the problem a bit easier, right? And then we delete all this, and the other one will still work, and the runtime will be fine. I don't know why I worry about the runtime so much. The runtime will always be fine because this is a very small problem. It's a very, very small problem. All right, let's try this one. All right, come on. Judging. Oh my god, did we got it wrong again? Oh my. What? Oh, we have a streak. 469. 461. Wait. Hold up. This is... We hit 168 in 2020. Now it hit 4 milliseconds. 57 test cases. 89 test cases. Wait, what the hell? The spread is gigantic. That is, I mean, the test cases are different, that's for sure. We have 89 test cases back then. And then we have 57. We changed the test case. I am confused. Very confused. And the two graphs look the same. If they change it, they should restart everything, right? They shouldn't use the same graph as before. I do not know what happened there. It's slow. I mean, it's very slow. Look at this one. Let's see. Search. Self.search. Isn't that the same? Max ij, that's fine. Next ij, if next set is this, I set it to this and I search it. If search is good, I return true. And after I return true, I reset it. It's a different position to do the backtracking. This is actually a better way to do backtracking if you think about it. Right? It's a better way. We set a backtracking the next one before the next one starts. And the current solution is we set the backtracking at the current spot, So we have to set it both times. This only set it once. So the search function is exactly the same. We have a quick check. Ooh, a quick check. I think that makes the difference. Board count. We counter it. And we chain. Oh man, chain again. I have to read it up. Word count. If I see. Yeah, it's the same method, but we didn't do a pre-processing. Yeah, we didn't pre-process. And actually now I realize these two can combine, right? I don't have to waste this much. All right, so this one, what should I say? So the method is to first identify, right, the position, the position of the letter in board that matches the beginning of word. Then from there, we simply run a DFS with backtracking to check whether we have a matching path to word. Now, one thing to keep in mind that we should not cache. Because the result of matching or not from any position on board is dependent on the previous path, right? If the previous paths are not the same, then we cannot use the memoized value of the current position. So this one will run. Ooh, what is the runtime? I probably asked exactly the same thing last time. I still don't know. Well, O(n) squared to get this, right? And what is this? What is such? I mean, what we're saying is each position we can branch out 4. Each position will branch out 4, right? So what, 4 to the n? I don't know, man. I don't know. I don't know. I have no idea. What's the runtime? God, I have no idea. I probably said exactly the same thing last time. That I have no idea about the runtime. Solution is locked. I want to see the runtime. DFS, TLE, backtracking. They have their runtime. They report the runtime. Passport by reference. Oh, for sure. I just want to see anybody mention the runtime. Well, most votes. Very short, no additional space. Yeah, I don't know. What's the runtime on this? That one's published the first time. And I think he does not want to do, oh, okay, here. Potentially this. Mm-hmm. Mn times 3 to the k. 3 to the k. Okay, 3 to the k. So, yeah, I have to check. Because, okay, I know how that arrived. So, basically, what we're saying is, because the word length is k, so we have to go k steps. We call it k steps deep. And each step we have 3 positions to go. Okay, so that makes sense. Time complexity analysis from deep chip is O m times n times 3 to the k, right? Where m, n are the number of rows and columns of board, and k is the length of word. It's 3 to the k instead of 4 to the k because at each level of DFS, we can only access, right? Only access 3 directions. Okay, so one more trick. So let's record this one. This one goes with, oh Jesus, this one goes really low, 4,000. This 1 millisecond. It does rank in 91%, but doesn't make any sense. All right, let's do solution 2, which is exactly the same. Right, solution 2 will be exactly the same. So solution 2. I have done this problem in July 2020. Then I submitted a solution. I submitted a solution with a pre-check, with a smarter pre-check that I think resulted in significant improvement, right? Improvement in time. So this solution is exactly the same as solution 1, except that we will add the pre-check. Alright, so before we use that, because I know I have to use chain, Python, this is what? itertools, chain. I forgot chain. Wait, this is the library. Alright, chain. What does chain, wait. They changed the, oh wow. They changed the font. Okay. Make enter the returns elements from the first verbal until it is exhausted. Then proceeds to, so we are talking about expanding them, right? Okay, so we are taking everything out. Therefore, if we use chain, we want to counter this entire board. That's what we want, right? Use a counter for the entire board. So what we want is take everything out, which means we're gonna destruct the board, that's going to give us 3 rows. We destruct the board. Do we need to destruct the board? Yes, we need to chain it. Right? So we destruct the board, become an iterable of 3 rows, and then we chain them. Then we'll get everything out of each one. Yep, that's pretty smart. So it's a tools, import, so we need a counter. Wait, that's not it a tool. That's collections. That's chains here. So from collections, import counter. So these are the 2 things we need, and then we don't need a potential start. Oh, then we're gonna do it differently. All right, let's just do exactly the same as what we did in the past. Here we go. So first of all, we're gonna say board count and use the same word. Board count equals counter. All right. I'm gonna chain it. Destruct board, and then word count will be counter word directly, and then we're gonna say for letter in letter count in word count dot items, right? Now we just say if board count letter is smaller than C, return false. Right? That's the first check. Once we're done, now we can talk about this. Right, now I'm going to do this. Then we go here. I'll do this. I'll do this. Blah blah blah. If this equals to this, then we're going to say if such ij1, right, return true. Otherwise, return false. All right. Say solution 2. Okay, that'll pass. Yeah, let me double check if we got it right. We should have some confidence, man. Have some confidence. That's, of course, we're gonna try to run it first. See if everything works here. Yeah, everything works here. Yeah, we check everything to see if the counter is good. Okay, submit. I expect to be very much faster. Yup, look at that. Look at that. Shaved off. Oh, that's the same. So they either increase the size. That's what I believe. I think they increased the size. And then they didn't really change. They forgot to change in the description. That's what I think. They increased the size. So look at the runtime. When we add the pre-check, we shaved off about a third, right? And then now we shaved off. It's actually about a fourth. Yep, this one is much faster. So with the pre-check, we reduce the runtime to 1,020 milliseconds, which gives us a 97%. All right, it's good. It's good practice. Although the problem done before, but it's good practice. I think the most important takeaway from this is be careful with caching, right? Be careful with caching. The truth is that caching is usually good, but in this case, it's not, because I'm pretty sure previously I didn't cache, not because I realized this, but just because I forgot about caching. And today I remembered about caching, but I used it wrong. You're not supposed to cache. And another is just the trick of doing the backtracking. I mean, we can do it a little better way, but it's fine. It's fine. All right, that will be it for today. I will see you guys tomorrow. Adios.